Imagine space-time as a deep river guiding every path. You are a small boat drifting where the current turns. Gravity is not a rope that pulls from far away. It is the flow that shapes motion already underway. You feel heavy because the ground pushes you upward. Astronauts float because nothing pushes them during freefall. To understand that feeling, we need a clear map. We will sail from Newton to Einstein with real checkpoints. Newton started with a simple rule about attraction. Bigger masses pull harder, while greater distance softens its grip. That rule explains falling apples and circling moons. It predicts everyday paths with reliable accuracy. Orbits are continuous falling that always misses the ground. Forward speed keeps a curved path that never lands. Energy gives another way to picture motion. Climbing trades speed for height while falling gives it back. Push fast enough and you leave the valley entirely. Escape velocity is simply clearing the gravitational well. Yet Newton's map cracks near extreme speed and density. Those edges demanded a deeper story about spacetime. Einstein replaced the idea of a pull with geometry, mass and energy curves spacetime, and curves guide motion. Free fall follows the straightest possible route in that geometry. Physicists call this natural track a geodesic. Stand on a scale and you feel weight from the floor. Remove the floor and the scale reads nothing at all. A rocket that accelerates upward feels like gravity inside. This perfect mimic is the equivalence principle. The rubber sheet model can help build intuition. The real curvature lives in space and in time together. Curved time changes how clocks tick near mass. Lower mass, clock runs slower, while higher mass, clock run faster. GPS only works because we correct those offsets. Your phone would drift far without that relativistic fix. Light has no rest mass yet. It still follows curves. A solar eclipse revealed star positions shifted by gravity. Today, telescopes find arcs and rings around galaxies. Gravity turns them into lenses that magnify distant light. Because gravity varies across distance, it raises tides. Near and far sides of Earth feel unequal pulls. Between large bodies, there are delicate pockets of balance. Spacecraft can loiter efficiently at these Lagrange points. Spinning masses twist the fabric like a slow whirlpool. Gyroscopes nearby precess because spacetime is being dragged. Mercury's orbit turns slightly more than Newton allowed. Curved spacetime explains the extra precession cleanly. Pack enough mass into a tiny region and curves steepen. A black hole forms where no outward path survives. Matter falling inward heats and shines before the horizon. Magnetic fields can launch jets that span galaxies. Crush a massive core without complete collapse and neutrons dominate. The result is a neutron star with blistering hotspots. Some neutron stars sweep radio beams with clock-like regularity. Pulsars time the cosmos with astonishing stability. When compact giants collide, the fabric itself ripples. Detectors hear their rising chirps as gravitational waves. The first clear detection arrived in 2015 from black holes, space rang, and matched the equations precisely. When neutron stars crash, they forge heavy elements like gold. The light we saw confirmed those nuclear predictions. Gravity also sets boundaries for keeping moons. A region called the Hill sphere marks each planet's domain. Come too close to a giant, and a moon can be torn apart. The Roche limit shreds it into arcs that can become rings. Spacecraft can trade momentum during planetary flybys. Gravity assists steel speed to reach distant worlds efficiently. Zoom out and watch gravity weave the cosmic web. Galaxies gather along filaments while vast voids grow between. Cosmic expansion stretches the grid on the largest scales. Gravity still wins locally where structures are bound. Some mass does not shine, yet deepens the wells we map. Lensing reveals dark matter through its quiet influence. Even radio signals slow slightly near heavy objects. The Shapiro delay records extra time along curved routes. At tiny scales, gravity still resists unification with quantum rules. The two great theories speak different dialects. Some researchers hunt a particle of the field called a graviton. Others quantize geometry itself into discrete loops. Whatever the final story becomes, the tested parts already work. Rockets navigate and land because these equations hold. Atomic clocks whisper the curvature of time with every tick. Satellites listen, and your map never loses the path. So return to the river that carried our story forward. Mass shapes the flow and everything follows its lines. You are not pulled by invisible strings across empty space. You surf a current that turns gently and sometimes plunges. From apples to black holes, one idea ties scenes together. Mass curves space-time and motion follows those curves. If this voyage made gravity feel clearer and unified, like and subscribe, then share it with a curious friend.